In the previous lecture, we were discussing exponential growth and decay models using first order differential equations. We discussed a couple of problems from the daily life, how we can model growth and decay of population models. Now today we are going to, previously we discussed growth and decay. Growth, exponential, in fact, exponential growth and decay models. And decay models using first order ODEs. And plus, in the decay models, we discussed radioactivity, decay of certain substances, radioactivity. Today, we are going to extend these models, and those models are called logistic models or logistic equations, maybe. In fact, in certain situations, exponential growth and decay models, particularly the growth models, are not feasible due to the conditions of which environment exert on the models or the growth of the population. It's not visible properly. Is it okay? Can you see the screen properly? Okay, then. For example, in exponential growth models, the equation is, in fact, dp by dt is proportional to p. Means population of a certain biological organisms or any other thing is proportional to p. And whenever we remove this sign of proportionality, we put a constant here, k, which is constant of proportionality, and it is the rate of growth. Means growth rate. This is what? This is the growth rate of the population. Growth rate. Now, this model is not feasible whenever the growth is over the long period of time, because it grows exponentially. It is not practically possible that up to infinite time the population grows, because it is not possible, because the environment or the certain kind of resources, they exert conditions on the growth of population of certain thing. Okay. For example, you have a container where you're growing bacteria. A container can hold or can sustain maximum capacity of bacteria. When the container is full of bacteria, there'll be no growth. Okay? Or there are certain other conditions, maybe the diet or the whatever they eat. Okay, it is limited. Okay, a certain kind of substance or population. Let's talk about population. They have fixed amount of things to eat. Okay, for example, 1,000 bacteria. We put something to eat for bacteria for the maximum 1,000 bacteria. After 1,000, they do not have any diet to eat, so the population cannot grow. Okay, so certain kind of situations, in certain kind of situations, the environment or certain other factors, they put certain kind of conditions so that the population doesn't grow. So that is, in this case, this model is not appropriate. Okay. In this case, what we do, for example, this k is the growth rate, so dp by dt whole divided by p is what this is equal to k. This is the growth rate, the rate of change of population divided by the current population. This is what it gives us K, the growth rate. Now, we assume that the growth rate is not constant here. Here, the growth rate is fixed or constant. Now, we assume that this is not constant. And we say that it is d by dt, dp by dt divided by t is certain kind of a function of t. Okay, it's kind of function of t. Means the growth rate changes with respect to the population. Okay, when the population grows and it goes until certain maximum number, the rate of change may decrease. Okay, so here we assume that this is a rate of growth, but it is not constant. In this situation, what would be the model of growth rate? It would be dp by dt is equal to, we multiply p on the other side, pf of p. This. Now, this is our equation which can model the growth rate whenever the environment has certain restriction on the growth. Now, furthermore, what should be this growth rate function? Okay, it should have certain conditions on it. For example, whenever the population grows within the initial times, okay, when the time is not too big, okay, in the starting time, this function of growth rate, it should be equal to k. Means we can have p of 0 is equal to k. Means when the population is 0, or the initial population is, you can say that the growth rate in the start, okay, it is equal to k, and then whenever we have a maximum population, the growth is 0. Where m is the maximum population, where m is the maximum population, it is called carrying capacity. Carrying capacity means a certain number of bacteria can grow with the provision of certain amount of diet, okay, or meals, whatever. So this number of bacteria can maximum survive on the certain number of meals or diet available for those bacteria, or whatever the population is. So now, along with these two conditions, the easiest function of the growth rate, f of p, which we can assume is the linear function, okay, which satisfies these two properties. Now, if we assume that f of p is some kind of linear function c1 plus c2 p, it's an equation of a straight line. Okay, it's a linear function. Now, using these two conditions, we say that f of 0 is equal to k. It gives us c1 when p is 0. Okay, and it gives us c1 is equal to k. Okay, this one. And whenever that population has carrying capacity, or the maximum population, we put this is equal to 0, and this gives us c1 is k plus c2 m. Okay, Now from here, C2 is negative k divided by m. This is your second constant. So the linear function which satisfies these two conditions, it would be k plus k minus k divided by m, or you can say it is k times 1 minus 1 over m. Okay. Now, if you put this thing over here, the model becomes this is equal to k p times 1 minus 1 over sorry, यहाँ पे p भी आएगा, p आएगा ना, k m times p. So it becomes 1 minus p by m. Now this would be an appropriate model which models the situation where we have a maximum capacity of population. Okay. This equation is called logistic equation. Okay. Logistic first order differential equation. That is not population zero, in fact. This is not population zero. It's a rate of growth rate. Okay. The growth rate of that population will be maximum. You can say that. It's k. Okay. The growth rate is k. We put p is equal to 0 here, then the growth rate would be equal to k, and it gives us this model. This one. Okay. When the population grows and it reaches certain amount, it means you can say that it is near its carrying capacity, then the growth rate decreases. Okay. In the start of the growth of the population, the growth rate will be maximum. You can say k. In fact, this function, these conditions which we exert here, put here on this growth rate function is what? Whenever we have p0, this is here we have p, here we have f of p. Okay. When p is 0, the growth rate is k. It's a maximum. Whenever p increases and reaches its maximum capacity, the growth rate will be 0 here. Okay. Now this thing is, these are two conditions. Now the growth rate decreases when the population increases. When it reaches its maximum capacity, the growth rate will become 0. So growth rate is decreasing. It can decrease maybe quadratically in this way, or in this way, or in this way, which is the linear case. This is the linear case. The simplest is the linear case. It may not be linear. It may be something different. But for the time being here, for you people, we are assuming that this function is linear. If it is linear, then when p is 0, we have a maximum growth rate. When the population grows, it may grow in this way. It may decrease in this way. It may decrease in this way, or it may decrease linearly. When the carrying capacity reaches, when the maximum of that population is possible or reaches, then the growth rate will become 0. For example, कोई भी biological organisms, bacteria, or कोई भी population है, ठीक है? Definitely. Population cannot grow over m. Okay, that's why we are assuming that this growth rate function, it satisfies these two conditions. So that is the model which we obtain now, which is more practical than this model. than this model. But this model doesn't have any limit of the population. It grows over the time. Okay, when the time reaches infinity, the population reaches infinity. That is not possible. It never happens. Even in the case of human beings, ये तो नहीं हो सकता कि population infinity हो जाए. Definitely, there are certain restrictions. There are deaths of the people. There are other factors. ठीक है. इसी तरह आपके पास जब कोई भी population है, उसमें rabbits की population है या कोई हनी बीज की पॉपुलेशन है या कोई बैक्टीरिया है, उनकी जो डाइट आप प्रोवाइड कर रहे हो मैक्सिमम 1000 बैक्टीरिया को जो है ना वो पॉसिबल है कि वो पूरी हो. ठीक है. अब 1000 बैक्टीरिया के बाद जो बैक्टीरिया होंगे उनको तो डाइट ही नहीं मिलेगी, कोई खुराक ही नहीं मिलेगी. दे विल डाई. So there will be no more population over 1000 bacteria. So this model, logistic growth models are basically, they help us to model these kind of situation. Plus some other situation we'll discuss then later on. Or certain number of infected people in some kind of pandemic. For example, आपके LUMS में, if you have 1000 students, campus is closed, nobody can enter or leave. ठीक है, 999 या 1000 students हैं, एक student बाहर से आता है who is infected with corona or dengue or whatever. He started infecting other people. Maximum कितना infected होंगे? 1000. उसके बाद तो infected होंगे ही नहीं. So exponential growth models जो हैं, they fail here in these situations when we have an isolation of a certain kind of population. We'll discuss this corona model after this. Okay, now I hope you get it. If you have any question, you can ask. Let's discuss now this example and then we'll move towards बल्कि यही ले लें example. मैंने यहाँ पे लिखी हुई है. How does an epidemic spread? Example. यहाँ पे तो कोई भी epidemic हो सकती है, हम सिर्फ जो है ना कोरोना को लेते हैं. COVID-19 maybe. Suppose a student carrying a flu virus or coronavirus returns to an isolated college campus of 1000 students. It is assumed that the rate at which the virus spreads is proportional not only to the number X of infected students, but also to the number of students which are not infected. Okay. We have a college, we have LUMS, we have 1000 students, campus is isolated, nobody can enter or leave the campus. One student comes into campus, okay, who is infected with the corona. Now, the growth of infected people with corona is not only proportional to the infected people, but it is also the proportional to the non-infected people, because there are interaction of students. ठीक है, infected people जो हैं वो non-infected के साथ मिलेंगे, infected के साथ मिलेंगे. ठीक है, so that's how this disease spreads. Okay. Now in that case, if we assume that X of t or P of t is the number of students who's infected, okay, P of t infected students at time t, ठीक है, और maximum students कितने हैं? Max students कितने हैं? They are 1000. अच्छा, और जो एक स्टूडेंट आता है initially, means when t is 0, we have population 1. At time is equal to 0, if one student enters into campus who is infected, then it is initial condition. At time 0, we have only one infected student. Now, the rate of change of this population of infected students is proportional to what? It is proportional to P, which is the number of infected students, times the number of known infected students. Okay. So we assume that this rate of change of the population is infected to the product of infected as well as known infected students. In fact, we are assuming that this is the number of interactions of infected and non-infected students. Okay. Now, when you remove this sign, you would have some constant of proportionality. Okay. Now, I haven't read it completely. Now let's read the further part of this question. Determine the number of infected students after 6 days. Okay, we have to determine P at 6. We have to find it. How many students are there after 6 days? How many students are infected after 6 days? If it is further observed that after 4 days, infected students are 50. Yes. Now, the question is complete. So this is the information which is given to us, and we have to find the number of infected students after 6 days. If you have any question, you can ask me. Now, I told you this K should be known. If it is not known, we should be given some extra condition. Okay. Now, this condition which is given to us, this will help us to find that rate of increase of pandemic. Okay. And this is what we have to find, and this is what we have initially, and this is our model. And what kind of model is this? It is kind of logistic growth model. Okay, if you take 1000 common from here, you can have 1000 K P times 1 minus P over 1000, where 1000 is what? Is the maximum number of students or the carrying capacity. Okay, so this is kind of logistic growth equation where we have a carrying capacity. Now, you can solve it by using what? Separation of variables method. Okay. And then further 1 over P times 1000 minus P dP is equal to K times dt. You integrate on both sides and put a constant of integration C. Here you have to use partial fractions. I hope you know partial fractions of integration. After solving it, you will get the solution of the form this thing. You'll get this P of T is equal to 1000 divided by 1 plus 999 e raised power negative 1000 KT. Okay, this is what you have obtained. Plus, you have also computed the value of C, the integration constant, by using initial condition. Okay, integration constant can be computed by using initial condition. So what is the initial condition here? This is your initial condition. Okay, this is your initial condition. This is not initial condition. This will help us. What? This will help us to find this unknown growth rate. Okay. Now you use this condition P of 4 is equal to 50. What is this P of 4? By using P of 4 is is equal to 50. It gives us what? It gives us 1000 divided by 1 plus 999 times exponential of negative 1000 times k times here 4, because t is 4. Okay. Now you have only one. This is equal to 50. You have only one unknown in this equation, which is k. Okay. You can multiply this thing over there, and then simplifying, taking log, you can find the value of k. I hope you can do it. Now let's come to the second board. Oh. Okay, after simplifying that equation, we obtain the value of k. K is 0.9906 divided by 1000. Okay, this is the value of k. Thus, we obtain the solution becomes P of t is equal to 1000 divided by 1 plus 999 times e raised power negative 0.9906 t, because this k is negative. Okay, you will see, I think it's, yes, it's negative in the solution. It's not k, which is negative. Now, this is your solution. You have only t here, function of t, and this is the p of t. Now, you can compute p of 6. Okay, the number of students after 6 days were infected by corona. So you put here 6 and simplify, this will give you 276 students. Okay, after 6 days, 276 students will have positive corona. Okay, now, what about after 10 days? You can compute, and so on. Now, whatever the time is, after a certain time, this number of infected students will not increase. Okay, because there are only 1000 students. So in this case, the solution of this equation, logistic growth equation, the solution is this. If you plot this, it will be of this form. Here you have carrying capacity. The solution cannot cross this line. Okay. And if you have 0 here, then at 0, how many students are there? We have 1 student. It starts from here. Okay. When time is 0, the student is 1. So our function, this function should be like this. I don't know its graph, but if you plot this function, you would definitely have the graph of this kind. Initially, the growth rate is slow, but it grows up to maximum capacity. And then after a certain time, the growth rate will decrease. And it will eventually reach at 1000. Okay. So this kind of solution, it should be. Because after a certain time, after this middle point, the growth rate is increasing. Growth is increasing, but the growth rate is decreasing. Okay, at this point, when the carrying capacity reaches, the growth rate becomes 0, because there are no further people who could be infected. I hope you get it. If you have any question, you can ask me.
Sir? Sir, can we approximate the value of k to simplify our calculations?
We cannot approximate. We can calculate only. We should be given some other condition in order to compute the key. जैसे कि यहाँ पे given है कि आपके पास initially एक student है, after चार दिनों के बाद they observe, क्योंकि लम्स में जो भी स्टूडेंट इन्फेक्ट होगा वो डेफिनेटली कहाँ पे जाएगा, क्लिनिक पे जाएगा ना, लम्स क्लिनिक पे. तो यू नो द डाटा कि आफ्टर 4 days कितने स्टूडेंट इन्फेक्ट हो चुके हैं. So you have another condition which will give you the rate of infected people. Okay.
सर
And
वो तो
then
समझ
you
आ
can
गई है.
हाँ
सर मैं ये कह रहा हूँ जैसे आपने के की वैल्यू लिखी ना 0.996, तो हम अगर इसको अप्रोक्सीमेट 0.1 ओवर 1000 कर लें ताकि हमारी कैलकुलेशन सिंप्लीफाई हो जाए.
हाँ that you can do it, but don't round the figure of k. Use the exact values.
ओके
Okay.
सर.
Sir,
G. Any other question?
you're saying that in the graph, like our growth rate is reducing, right, as our population is increasing.
Yes.
So isn't K a constant?
Yes, it is constant. Yes, it is constant here, but the function, in fact, in real situation, the growth rate could be, you can say decreasing, but the graph of this function should be like this. Means initially at a certain time here, अगर यहाँ पे आपके पास time up to certain time, t final maybe, ठीक है. यहाँ तक हाफ टाइम तक जो ग्रोथ रेट होगा वो क्या होगा, मींस जो इन्फेक्टेड पीपल जो होंगे वो तेजी से इन्फेक्ट करेंगे, ठीक है, तेजी से इन्फेक्टेड होंगे. आफ्टर सर्टेन मिडल टाइम दिस फंक्शन will increase, but the rate of change of this function will decrease. The growth rate, you can say that, but the constant k is the k is constant here. Yes, that's true. The number of infected people, in fact, their rate of change will decrease, but the function still increases. You can see here in the notes I have provided you. After 10 days, 953 students would be infected out of 1,000. Okay. After 11 days, it will go towards, means near 1,000. Whenever you increase the number of days, this number of infected people will increase. But eventually, when t goes to infinity, you can put a limit here. I hope you know what are limits. In calculus, you must have discussed the limits. If you put a limit here, limit t goes to infinity, p of t, and here you put a limit, this term will go to 0 when we put a limit t approaches to infinity, because this will give us e raised power negative infinity. E raised power negative infinity is what? It is 0. So when it is 0, this will become, this whole factor will become 0. And what do we obtain? We obtain 0, 1,000, which is what? Which is the carrying capacity or the maximum number of students present in the campus. Another example is given here. A population of rabbits in a meadow is observed to be 200 rabbits at time t is equal to 0. After a month, the rabbit population observed to have increased by 4. एक महीने बाद 4 rabbits जो हैं increase होंगे. Using the carrying capacity of 750 rabbits, carrying capacity, maximum number of rabbits which can survive in that meadow is 750. And the growth rate is 0.04. Write the logistic equation and initial condition for the model. What will be the rabbit population after 1 year? After 1 year means after 12 months. So I hope you can do it. Try to do it. An improvement or an An extension in the logistic equation could be the minimum threshold of the population. Okay? It is possible to see at the minimum number of population it gives us. Basically, we can extend we can extend that logistic equation by another factor of this thing, where T is the threshold population, the minimum possible population of a species. Below that number of a certain species, we can put that species on in a danger zone, that this species, this particular species might be extinct after a certain period of time. So this equation helps us to model further growth of a certain population, okay, with the condition of the minimum threshold population T. Okay, you can see it, but I'm not going to details of this. This model you can see in my notes. In fact, T is the minimum number of population, which is basically mandatory for a certain kind of population to survive. Okay, जैसे कि whales हैं, at some time whales in the ocean, they were becoming extinct. Their population was very low because they were in, I think, early 90s, the whale oil was used in many daily life kind of applications in needs. People started killing those whales in order to get the whale oil. तो बहुत सारी whales उससे basically क्या हो गई थी, कम हो गई थी. फिर इन्होंने एक restriction लगा दी कि whale को मारना या पकड़ना जो है वो उस पे पाबंदी है. जैसे कि in certain situation गवर्नमेंट पाबंदी लगा देती है कि आपने certain कोई भी बर्ड है उसका शिकार नहीं करना. क्यों? क्योंकि दे आर बिकमिंग एक्सटिंक्ट. ठीक है, वो क्यों कंडीशन लगाते हैं? बिकॉज उनकी जो पॉपुलेशन है दे आर गोइंग टू बी एक्सटिंक्ट. जब आप एक पाबंदी लगा देते हैं, ठीक है, किसी भी बर्ड को या किसी जानवर को मारने की जंगल में, तो क्या होता है, उनको टाइम मिलता है टू ग्रो देयर पॉपुलेशन, so that that kind of particular population, that it doesn't become extinct. So this basically application, this model help us to take into account the minimum threshold population of certain species. Okay. So this was logistic growth equation. You can, it's a non-linear equation, but we can solve this kind of differential equation. It is, again, an autonomous differential equation as well, because the right hand side function, it involves only a function of dependent variable. It is autonomous first order ODE. It is non-linear. We can solve it by using separation of variables. Okay, and then we can obtain the solution. Yes, minimum critical point. Okay, below that population, that species could be is going to decay and it becomes extinct. So that's why we put certain kind of restriction on the environment in order to provide them certain time or space to grow appropriately. This was all about autonomous and then logistic growth models, exponential growth models, and you can use the direction field method to plot it. Okay, direction fields method, you can find the critical points of these logistic growth equations. You can plot a phase portrait, and then you can analyze the solutions of these kind of equations. The next is a couple of applications related to economics and banking sector. I chose different fields to show you applications of first order differential equation. And now the banking side applications. Of first order differential equation. For example, saving for retirement. I'm doing job. I'll be retired after maybe 15 years. So I would definitely think about my retirement plan. I would definitely save some money per month or per year for my retirement so that I can have handsome amount of money at the time of retirement. So that's also give us first order differential equation. A worker saves, any worker or a worker of the company saves $5,000, $5,000 or rupees or whatever per year, and invest it or put it in the saving account, maybe. Okay, whatever he does, we don't know. And making 6% interest in annually. बैंक में डाल देता है सेविंग अकाउंट में, ठीक है, इंटरेस्ट उसको मिलता है 6% annually, 6% per year. Per year. How much will he or she have 30 years later? ठीक है, 30 साल बाद उसके पास कितने पैसे होंगे? It's a very simple model. Let us assume that x of t is what? It is his amount after a certain period of time. Okay. At any time t, you can say that. Okay. It's amount, saving amount, or the amount, you can say that amount at time t. Okay. इसके जो rate of change होगा, dx by dt is what? It is equal to two factors, this amount and this amount, because this is every year, okay, and this is also every year. It's not one time, it is not initial. Initially he doesn't have any saving. देखिए पहला साल जॉब करेगा तो जॉब के स्टार्टिंग में तो 5,000 नहीं होंगे ना उसके पास, तो इनिशियली क्या होगा? इनिशियली एक्स ऑफ जीरो क्या होगा? उसके पास जीरो होगा. ऑब्वियसली इनिशियली उसके पास कोई अमाउंट नहीं है, कोई सेविंग नहीं है. वो जब स्टार्ट करेगा जॉब आफ्टर 1 year he'll save 5,000. Initially he will have zero amount. So that is why that is an obvious initial condition. This is your initial condition. Now this is every year and this is every year. So dx by dt is changing on the factors which is changing every year. So this is changing every year, this is changing every year. What is this? It is 5,000 plus 6% of the amount, which is 0.06 x. X is the current amount. Every year it changes at a 6%, and it adds every year 5,000. So this will be your equation along with this initial condition. And what kind of this differential equation is? It is dx by dt negative 0.06x is equal to 5,000, along with x of 0 is equal to 0. So this is your model, which is a linear. Yes.
8:45 हो गए quiz का time.
Okay, thank you. This is linear first order differential equation. Now, after solving it by using integrating factors, You have to use integrating factor here in order to solve it. Once you solve it, you just have to put what after 30 years? Yes, in question, what amount will he have after 30 years? After solving this differential equation, you just have to put t is equal to 30. You'll get the amount after 30 years he will have after the retirement. And it is how much? 4,20,802. ठीक है? X of 30 क्या होगा? X of 30 is उसके पास $420,802 होंगे. $4,20,802 होंगे. Okay? So this is how we can model saving for the retirement. Bank account balance, and there are a couple of more applications here. How to model the CP fund of an employee. We'll discuss it in the next lecture. Let's start quiz now. If you have any question, you can ask me. Quiz will start at 8:45. It's on LMS.